Hello everyone, my name is Dr. K.C.H. Apparao, working as an associate professor in mechanical engineering department. Okay, in previous class we discussed the uh, important questions which are on condensation and boiling. So in this class we'll see different problems which are based upon the or which are related to boiling and condensation. Okay, we know that boiling and condensation. Boiling is the boiling and condensation. We already discussed in previous class. So we know that convection. Convection is the process, one of the mode to transfer heat from solid to liquid or solid to fluid. Okay. So along with phase change occurs. So that is nothing but boiling and condensations. So in natural convection or any convection, we will see only heat transfer rate. But in boiling and condensation, along with heat transfer, and we will see the phase changing. So in boiling, the liquid is converted into vapor. In condensation, the vapor is converted into liquid. So here heat is transferred, and heat in boiling heat will be taken in the form of latent heat. So that latent heat will be taken to change the phase. In condensation, that latent heat will be given to solid surface. Okay. You will see the first numerical, a wire of 1.2 diameter and, and, and 200 length is submerged horizontally in water. So at a so 7 bar pressure. So the wire carries a current I is equal to 135 amps with an uh, amplified voltage V is equal to 2.18 voltage. So current and voltage have been given. So this current and voltage, uh, the heat will be produced. We know that formula because rate of heat transfer Q is equal to voltage into I, current into voltage or voltage into I. So if the surface of the wire is maintained at surface temperature also given, Ts is equal to 200 degree Celsius. So this is the data. So has been given in this numerical. First you have to find out the heat flux. Next boiling heat transfer coefficient. Okay. So first we'll find out the heat flux Q. You know this formula, voltage and current both are given, so you can multiply both of them. So current into voltage, then you can find out the Q, so rate of heat transfer. So then if you know the rate of heat transfer, then you can find out the heat flux. What is heat flux? Heat flux is nothing but a small q, so q by area. So area of the wire has been given, diameter and length also given. Area is equal to 5 dl. You can take, convert it into diameter and length should be converted into meters. Okay. So by using these formulas, we can find out the heat flux. Then boiling heat transfer coefficient also we have to find out. If you know the heat flux, Q is equal to H into the temperature difference. T saturation, solid surface temperature, and minus saturation temperature. Okay, we'll see here. Uh, First of all, diameter value is 1.2 convert into meter. So length of the pipe, that is 200 0.2 meters, and amperes, current value is equal to 1351 amperes, voltage value is equal to 2.18 voltage. So surface temperature Ts is equal to 200. This is the given data. First you have to find out the rate of heat transfer Q, passing heat voltage into I. That voltage is equal to 2.18 into 134. Okay. So this is 294.3 watts. You know this one. So then you can find out the area. So this is pi dl. How to add the pi. Okay. So the area of this y, that is area is equal to pi dl. Pi into d is equal to 0.0012 into L is equal to 0.2. So this value is equal to 7.54 into 10 to the power of minus 4 meters square. So this is the area. Then you can find out the heat flux. Heat flux is equal to Q by A. So 0.39 into 10 to the power of 6 by area. So what is the area? The area of this one is equal to 7.54 into 10 to the power of minus 4. So Q value is equal to 294. Okay, so this is not Q is equal to the value of Q is equal to 294.3. If you substitute these values, we can find out this heat flux value. Heat flux is equal to 0.39 into 10 to the power 6 or 0.39 megawatts per meter square. So next, boiling heat transfer coefficient. Boiling heat transfer coefficient H is equal to formula. You know that heat flux is equal to H into temperature difference delta T. So then H is equal to Q by temperature difference, solid surface temperature minus saturated surface temperature. So H is equal to Q. So Q is equal to, you know that we already solved that one. We got that value 0.39 into 10 to the power of 6 by Ts is equal to surface temperature. So that is 200 minus T saturation also given, that is 164.97. Then the value of H heat transfer coefficient is equal to 1133.3 watt per meter square. Okay. So we'll see one more numerical which has been given in question bank. Okay. So an electrical wire of 1.25 mm, so diameter of wire has been given, and 250 mm long, length also given, is laid horizontally and submerged in water. So water at atmospheric pressure. The wire has an applied voltage. The voltage of the wire is 18 watts and carries current I is equal to 45 amps. Okay. So if you know that voltage and I, then you can find out Q. Q is equal to V into I. Okay. So then if you know that Q, capital Q, then you can find out heat flux. Heat flux is equal to Q by A. Okay. So by using this form, you can find out. Next one, the excess temperature also you have to find out. Excess temperature delta T, delta T excess temperature, it is represented by delta T. So we have to find out this value. So the boiling heat transfer coefficient, you know this formula, you can use this one. H is equal to 1.5 into Q by A to the power of 0.75. So by using this formula, you can find out the H value. Okay, so the correlations, the following correlation for water boiling on a horizontal submerged surface. So D is equal to diameter. So this is the data what is given here. D is equal to 1.25 mm converted to meters, and I, this is the length of the pipe to 250 mm, 0.25 meter. Voltage is equal to 18. Current is 45 amperes. So heat flux we can find out. First of all, we have to find out the Q value. So Q is equal to V into I, voltage into current. So that one is 18 into 45, 810 watts. So then you have to find out the surface area. ES is equal to pi dl. So you know that pi into d, diameter 0.00125 into L also 0.25. So this value is equal to 9.81 into 10 to the power of minus 4 meters square. Okay. So then you can have to find out small q is equal to big Q by area. Okay. So then we'll get the heat flux value. So heat flux value is equal to 0.825 megawatts per meter square. So next to the excess temperature. So delta T, that is nothing but surface temperature minus saturation temperature, T saturation. So we have to find this value. Okay. So using the correlation, so this correlation you can find out the value by using this correlation from the data book also. Then you can find the value. So you know that Q value, EA value also, you have to find out the delta T value. So then delta T is equal to, this is the formula. Okay. If you substitute the value of heat flux, so small q, then you will get the temperature difference. So delta T, excess temperature difference, delta T is equal to 19.68 Celsius. You can take this. We'll see one more numerical. The nickel wire of 1 mm diameter and 400 mm long. So carrying current is submerged in a water bath, so which is open to atmospheric pressure. So calculate the voltage. We have to find out the voltage at the burnout point. So we know that the burnout point is the critical heat flux point. So if at this point the wire carries a current, so current value I is equal to 190. Voltage you have to find out. You know that critical heat flux formula. You can collect this one from the data book also. Okay, so this value is equal to critical heat flux 0.18 into rho V vapor density to the power 1 by 2 into alpha Fg into G acceleration due to gravity, sigma surface tension, density of the liquid minus density of the vapor to the power of 1 by 4. So by using this formula, you can find out the critical heat flux. Okay. So if you know the critical heat flux, then you can find out the V value. For that V value, because QSC is equal to Q by A. Then Q is equal to Q critical heat flux into area. Into area. Okay. So then you know that the Q is nothing but voltage into I. Voltage into I is equal to Q critical heat flux into area. You know the parameters, this one also. Then you can find out the V value. So here we'll see how to find out this numerical. So this is the given data, diameter, and so that is the diameter is equal to 0.001 meter. So because 1 mm diameter converted into meters, length L is equal to 400 mm converted into meters also. Next to current value, so I value is equal to 190 amps. So thermo physical properties of the water, because here density of vapor and density of liquid, enthalpy, so all these values are surface tension also there. So we have to collect these properties based upon the temperature. So what is the given here? you know that water and vapor temperature, saturation temperature 100 degrees Celsius, you can take that one temperature. So at this temperature you can take the properties, the thermophysical properties of water and vapor, so at 100 degrees Celsius. So then rho L, liquid and vapor, both densities are equal. The density is equal to 958.4 kg per meter cube. Okay. Liquid and fluid. So this is liquid and fluid. Next to vapor. Okay. Vapor density is equal to 0.5955 kg per meter cube. Enthalpy HFG is equal to 2257. Surface tension is equal to 58.9 into 10 to the power minus 3 Newton per meter. So this is the data you can collect from data book with respect to the temperature of vapor and water. So first, voltage at the burnout point. So burnout point means critical heat flux. So you know that formula, critical heat flux formula. So 0.18 into rho v to the power 1 by 2 HFZ into uh, G sigma rho L minus rho v to the power 1 by 4. So here rho v, you know that HFG also, G and surface tension, you know that all the values, you can substitute the values. The properties which are taken from the data book, we can substitute all the values, so then we will get the final value, that is the heat flux, critical heat flux, Q SC, critical heat flux is equal to 1.52 megawatts per meter square. So this is the value. If you know this value, then you can find out the um, Q value. Because small heat flux is equal to Q by A. Then uh, Q is equal to heat flux into area. Okay. If you know that area, then um, then you can find out the Q value. So, but Q is equal to, already know that V into I. Then you know that I, then you can find out the V. Okay. So in this way, just you can find out the QC. The voltage is equal to 10.05 watts. So next, a vertical tube of 60 outside diameter and 1.2 is exposed to steam at atmospheric pressure. The outer surface of the tube is maintained at a temperature of 50 degrees Celsius, okay, by circulating cold water through the pipes. So calculate the rate of heat transfer to the coolant and the rate of condensation. So this is the process process of condensation. So previous numericals related to boiling. So from this numerical, we will see condensation problems. Okay, first we have to find out the Q value, then rate of condensation. So M value we have to find out. So what is the data given here? So Q diameter, tube diameter, vertical tube. So diameter is equal to 60 converted to meters. Next to length also given 1.2 meters. Just next to surface temperature 50 degrees Celsius, that one also given. Then the mean temperature of the film. So you know that surface temperature, you know that the saturation temperature of the liquid. Okay. So 100 degrees, 100 plus 50, so 75 is the value. At this temperature, we can take the properties of the water and properties of the steam also. Okay, so this is the properties of the water: royal, liquid density, and dynamic viscosity of the liquid, and the thermal conductivity of the liquid. So properties of saturated vapor. So that is rho v density and enthalpy HFC is equal to value you can take this properties, and then you can solve the first rate of heat transfer. For this one, uh, you have to find out first H bar, because Q is equal to H bar into area into uh, T saturation, because vapor temperature is very higher than the surface temperature. T saturation minus Ts. Okay. So by using this formula, what was derived in previous classes, so H bar is equal to 1.13 into rho L minus rho V into KQ G HFC by mu L, dynamic viscosity into length of the pipe. So all the parameters we know that because these parameters or these properties are taken from the data book with respect to mean temperature. You know that the density of the liquid, you know the density of vapor also, thermal conductivity of the liquid, you know this one. If you substitute all the values rho 1, rho L, rho V, and thermal conductivity G 9.81, HFC 2257 into 10 cube. So next to dynamic viscosity and length and T saturation 100 minus T surface is 50. Then you will get the H bar. If you know the H bar, then you automatically can find out the rate of heat transfer. H bar into area into temperature difference. T saturation minus T solid. Area is equal to pi dl. If you substitute all the values, you will get the rate of heat transfer. So in this way, just we can find out the rate of heat transfer in condensation also. Okay. So next to rate of condensation of steam. So M value, mass flow rate of condensation. The condensation rate is equal to Q by HFC. Okay. So enthalpy. So Q by HFC. If you substitute the values of HFC and Q, then we will get the mass flow rate, condensation rate of condensation we will get. So 83.52 kg per hour we can take. Now we have to check the assumption of laminar flow. So initially we started with the flow is laminar flow. Based upon that one, we have taken the H bar formula. Okay. So Reynolds number is equal to 4 mm by perimeter into dynamic viscosity. Okay. If you find the RE value, Reynolds value, then automatically you can identify which type of flow. Okay. So here Reynolds number is equal to not Reynolds number, Rayleigh number. Okay. So based upon this number, so if less than 1800, the Reynolds number is the Reynolds number is less than 1800, so then the flow is laminar. If the greater than 1800, because it is 5, it is greater than 1800, so that shows the turbulent flow. So okay, because we started with the this is the from for laminar condensation on a vertical surface. Okay. Because of that assumption, we start that. Next, one more numerical will see a vertical plate. So height of the plate is 350 mm and 420 wide is maintained at 40 degrees Celsius and is exposed to saturated steam at 1 atmosphere pressure. So calculate the total heat flux. Only total heat flux you can find out. Okay. So you know that given data, surface temperature, saturation temperature, length of the surface, and width of the surface also given. The properties will be evaluated at the film temperature. Film temperature means 100 plus surface temperature 40 by 2. So 70 degrees Celsius. Just we can take the properties. Okay. So the properties at 70 degrees Celsius, rho L liquid density, dynamic viscosity, and the thermal conductivity and HFC also we can take this one. So by using this parameter, we can find out the first H bar. H bar. H bar is equal to 0.943 rho L into rho L minus rho V. So here rho V is very less, very less compared to rho L, density of the liquid. So you can neglect this one also. Then the formula will be like this one. So rho L square K cube G HFG by mu L into T saturation 100 minus Ts is the 40. Okay, if you substitute all the values, then you will get the H bar. If you know the H bar, then automatically you can find out the Q value also. Rate of heat transfer. So H bar into area into T saturation minus T. Yes. So by using this formula, you can find out the Q value also. Here you can see. So this is the formula. So if you substitute the H bar and area values and T saturation and T surface, you will get the value that is nothing but 43.494 kilowatts. Okay. So these are the numericals which are given in the question bank. You can check this one. These are the textbooks for the reference I have given. Thank you. Listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.